Hello everyone. So welcome to my YouTube channel Akasting. So in today's video, what we will cover is we'll go in the advanced stage of the data types numbers. So we'll try to learn or explore more in detail what is happening in the different numeric data type, the int, float, and the complex. So with that, let's get started. So here I have opened my Jupyter notebook and I have already created the code for this. So let's go through it one by one. So if you remember, in my previous videos, I have already covered a high level overview and a high level or basic understanding of each of these numeric type, how to declare that in Python. So you can refer my previous videos on this. And I have also explained how the memory allocation is happening whenever we are creating a single integer or a float or a complex. Generally, like for integer, it's around, I think, uh, 8 into 4, while for float it's 8 into 3, and for complex it is 8 into 4 again, which is my white, you can say. So here, like, one is for reference count and then counter, and then rest is for our the digits that we create. So we have like around 8 bytes or 64 bit fixed for that. And since here we have two different real and complex digits, so that's where it is 64 into 2 and then plus 8, which is like fixed kind of component. Similarly, for int, we have 8 plus 8 plus 8 plus 4, which where this 4 keeps on extending. So generally the minimum is 28, not 8 into 4. So this is how the memory storage looks like whenever we are creating a very basic or very small these data types. Now in today's video, also we have covered about this type conversion, how we can convert one data type into other data types, especially from the cascading effect. Like we can convert int to float and float to and float and int both to complex, but reverse it's difficult to come back. We can do it for float to int, but for complex, I think we can't do that. So that's where we also learned about the difference between int and round, the chopping operation and other things. So you can also refer a special video on that I have uploaded. Now in today's video, we will try to understand a little bit deep into each of these, uh, the data types, int, float, and complex. And let's try to start it. So let me go a little down. So yeah, here you can see what I have written. Unlimited precision. So in Python, integers can grow as large as your system memory allows without overflowing. And you can define integers in binary, octal, hexadecimal, and other formats as well. So for here, I have covered just the binary one, but it can be created via octal or hexadecimal, which we rarely use. Even binary we rarely use. So most of the time we directly create the numbers. But still, I will try to show like how we can convert from binary to uh, binary is basically base 2, which is based on 0 and 1, because our different you can say like the logic gates that is there in the memory or CPU, so those works on this two, either 0 or 1 it can store, switch on, switch off, so like that. So that's where this base 2 comes, and this binary is in base 2, and whatever numbers that we try to understand, it's in base 10. So we'll try to see that also, which numbers and why base 10 and how to convert from base 10 to base 2. So these things we will try to see. Now first let's try to understand this unlimited precision, where which we already covered to some extent. Like if you remember, we have already seen how we can keep increasing the integers, and that too with a very high precision. Like it won't be like approximation, but it is the exact count. So here you have, like I have shown you, like we can create a very small integer 1 to 3, or we can create a million or billion value in integer, and then we can also create hundreds of zero in an integer. But then we also learned that there is a system limit of this 4300 digit. So if we want to go beyond that, we have to specifically get like set the system limit or increase the system limit. So we have tried to use this function to increase the system limit of defining an integer, right? And here we also had this command to check the size of my integer basically. So this is what we already learned about. So after resetting, we can go till 5,000 or to any values, because this in Python we can define integers to very precise value in any high details, like as big number as possible. So that's where we are going to see today. So uh, this one we already created. Now today we will try to add one more add extra numbers today. So instead of 5,000 we will try with 10,000 and million or 10 million, and see how the things will change. So for example, if I try to define this as an integer which is like around 10,000 power of 10, so it will run for sure. So if I just run it for 1000, let's see how long it takes. It takes hardly a second. And if I define it for 10,000, it is also taking very less time. And as I keep on increasing, what happens is, like, since integer is defined in that way, the kind of memory that it consumes, the last piece basically, it comes with three things: first box, second box, third box, and fourth box. So this fourth box, these are 8 bytes each, and this fourth box is 4 byte, but it keeps on increasing as we increase our number size. So that's how it is. So whenever we are increasing this, the size of this total number will also keep on increasing, and that we can check dynamically here using the command that we have. So this one. Now, yeah, let's try to check this size. So you can see the size of this. I need to import the system library. So yeah, around 44,000 bytes, which is around 44 MB. So this is consuming. Now, if I increase it further, you will see for a 1 million, the size is how much? See, it went from 40 MB to 400 kilobyte. Sorry, not MB, but kilobyte to 400 kilobyte. Now, if I further increase it, it will slow the process now. See, it takes some time now. Instead of 1 second or less than that, it took around 5 to 6 seconds to compute it, and the size also increased. So you can see now the size is around 4 MB, we can say, instead of KB. So as we keep on increasing, of course, we can define it to in very precision. There is no doubt about that. Python offers that, but it becomes really computationally, I think, difficult to calculate the calculation over it. So if I try to apply a factorial, let's say I have this function from maths. There is a math library. I'm just using it. You don't need to understand, but factorial is nothing but it try to calculate the value. So for example, if I want to calculate factorial of 4, it's like 4 into 3 into 2 into 1, which is nothing but 24. If I want to calculate factorial 3, it will be 3 into 2 into 1, which is 6. So this way factorial works. So if I define if I try to calculate the factorial of 10,000, or let's say 1,000, it will happen very fast. See, but if I increase it to 10,000, then the things starts going slow, or even it fails. See, it is saying like exceeded the limit 4,300 digit, and we need to change the digit setting. So this setting that it is talking about. So once we set this limit, now if we run it, then it will run. So we basically extended the limit to which a integer can be defined. And similarly, if we keep on increasing, so it will start taking more time. See, now it is taking more time. So this is where if we are doing multiple such calculations, and especially in data science or in some other thing, then you can see just with 1 million integer whose value is 1 million, it took around 3 seconds. So you can imagine like it will take 10 folds or more than that to calculate uh, for a number as big as this. Or it may just keep the system busy always, and it won't allow us to do anything, or it will just crash the CPU. So that's the complexity if we are going to define a very big number, although we have this facility. But yeah, so yeah, so this was the special thing that I wanted to talk about in integer. So we should be very much considerate while defining a very big number, and this integer precision is there so that we can, whenever we are defining epoch or basically any integer we should try to define, it should be very precise, and that's where uh, Python is offering this functionality. Again, why this system this is like so accurate, and when we will talk about float you will see that this is not that accurate. It is like rounded off to at least certain place. So the thing is like in integer we just want to get the very precise value, and that's where it is kind of you can say software based computation, not hardware based computation, where like the software is handling the storage. So whenever the number size is increasing, it keeps on storing it in different memory, and it internally try to handle or manage those memory data and try to do the calculation using those. So that's how this integer keeps on expanding. But in float we have this limit that it will stay within 64 bit, it won't go beyond that. So we'll check that. See, let's go to that now. Yeah, you can see I have written in the first line itself that unlike integer, floats are constrained by standard 64-bit hardware limitation, meaning minor rounding limits apply to extremely precise fraction. So there is some rounding that is still applicable to floats. It's not like we are going very precise. Again, why do like in like integer you may think like why we need to go very uh, accurate, while in float we don't need to be very accurate, but we can have this limitation and precise rounding also. So why is that? So whenever we try to calculate a float, it's nothing but kind of ratio 1 by 10 or 5 by 10, so something like this. So whenever we are trying to calculate it, it is around zero point 0.2, it is around zero point 0.1. So we don't want like very much details about it. That is the one thing. If it's like this, like in very less scenario or very less use cases, we need this much accuracy. Maybe in scientific scenarios or in space missions or kind of those places where that nano and below nano granularity is needed. But in most of the case we try to chop off and we just use the round of figures to meet the objective that the business challenge offers most of the time, and that's where rounding makes sense. But for a number we need it to be very precise so that we don't mix up and we don't end up generating a kind of wrong float also. That is also a possibility. So that's where it's mainly this is hardware based, and it is limited by the hardware constraint that we have in the system. So this is the basic difference. So in int and in float, this is int is software based and this is hardware based computation, and that's why this is very fast while int is a little slow because it handles everything in between. So that's where it becomes slow. But float is like Python's float is very fast, and since it is directly computed on the chipset, so directly with the hardware, so it's really fast, and that's why. And we also need it to work faster so that we can leverage it most of the time. So that's why. Now let's try to understand one of the case which often like we face. So for example, if I want to sum this zero point 0.1 and zero point 0.3, so generally what happens? If I sum two number like 2, 1 plus 2, it will give 3. And when I try to check if it is equal to 3, it will give me true. See, now when I try to do the same thing with this, what happens if I try to run it? It will give me false. And when I try to check why it's false, let's try to run this. So it gave me false. Now if I just try to do it manually, the sum. So let's try to calculate the sum here and see what is getting. So you can see it's not zero point 0.3. It's a rounded figure and it is going very deep in precision. So it's around 0.000 and in the end we have 4. So that's why it's not same zero point 0.3 and zero point 0.4. And why this zero point 0.4 like point like 0.0 and in the end why we are getting 4, and if we try to see it for 3, let's say zero point 0.3, it is working good. But if I try to check for zero point 0.7, you can see still there is some uh, extension is happening. So why this thing is there? So if we try to understand, it's like we have this function in Python which try to tell me the exact ratio that is creating this number or this float. So if 1.0, how this is created, it will tell that 1 divided by 1. So 1 by 1 is 1. So you can see here we have some examples as well. So what is 10? It is 10 by 1. What is 0? It is 0 by 1. What is 0.25? It is 1 minus 1 by 4. So similarly, for any number, we can check this. Now let's try to check it for 0 0.5. You can see 1 by 2. But when we will check it for zero point 0.1, it will give a very different number. You can see. Now, if you take this number and try to divide it manually, let's see the value that it gives. See, it's coming 0.1. And if let's see if we don't round it. Okay, still it's 1. But this is telling me the exact number which it is trying to divide and which is generating this 0.1. So that's where, since there is a precision involved, like the number is so big, so when you will try to divide, for sure it's not going to become 0 in the end always. There is a chance that some reminder will be there, and based on that we will get some value. So that's where this extra 0.4 is coming up, because it is dividing a very big number. It's not like it is doing 1 by 10, but it is dividing these two numbers. And these two numbers are based on the precision that the 64-bit offers. Now, for quick check, we can also check the size of this number just for yeah. Let's see what is the byte. So you can see 32 byte. 32 byte is nothing but the limit to which our float can go, right? Now this is clear, and you can check it for some other numbers as well. So if I check it for zero point 0.2, I am still getting very big numbers. If I check it for zero point 0.3, very big number. But when I will go for 0.5, you will see that the number will become very small, 1 by 2. So what it says, a kind of a high level, it's like it is using a 10 base scale. 10 base whose like fraction is 2 into 5. So 5 is nothing but 5 by 10, and 10 is nothing but 2 into 5. So that's where this is very precise, 1 and 2. So same thing, if we try to check it for any 5 base number, for example 2 5, it will again give me very precise. If I use 1 2 5, then also it will give me very precise. But if I change it to any other number like 0.15, you will see the numbers again increased. Why? Let's try to write the fraction of 0.15. This is like this. If I split it, 5 into 3 and 5 into 20. So this is not a factor of like 10, right? This is not best 2 or 5 out of like this is 3. So this is not like these two. And that's where it is trying to kind of make precise kind of accuracy around that. It's not perfect, but it is going as deep as possible to make the values look perfect. Something like that is happening, and that's why you are seeing these numbers so weak. Okay, so let's now try to cover some of the remaining topics here. So we also have this functionality in Python that the float here we can try to understand. While integers have infinite precision, floats have a strict maximum size boundary. This is what I was trying to say. So computers, operating system, and processors have hardware defined limits for how many base 10 digits they can reliably track before turning them into base 2 approximation. So what is happening here is like, as I explained, like base 10 and base 2. So whenever this is crossing that limit, it tries to convert it into base 2 from base 10, because it don't need to make that infinite precision, just like how it is doing for integers. It's try to follow a strict maximum size boundary. So maximum size boundary for float we already know, 8 byte into 3. So that's why it's try to follow in that range only. And here we can see that print the system rule for floating math. So like if I use this library and I try to check what is float info, so it will give me the full detail about how a float info or a like decimal number is defined in this Python. So let's try to see and run and check the maximum limit as well, and we'll go through each of these, and let's comment it for now. So you can see the maximum size to which a float limit can be defined is this 1.79 to the power 308. This is what we are also seeing here. If we try to go above this value, for example, this one, we have used power of 308. So it's for sure going to be fail, because this is long int too large to convert to float. So that's why it is going to fail. Now max exponential power is allowed is 10,024, and 10 base like base 10 max exponential allowed is 308. So yeah, you can go through these details, and it will help you understand like how this float and int is actually working at the backend. So we try to always use it from the high level, but uh, there is this thing which is happening at the back end, and it's always good to know these things as well, so that you don't get these kind of surprises while writing bigger codes or dealing with large data set. So you can see it is saying too long int to convert to float, so we are getting this error. Now we have this infinity and nan value in Python, which we can directly use. So whenever like we use this INF, either it is not case sensitive, we can use capital or small, doesn't matter. So that I have already written here. They are case insensitive when passed into string. So by this we define it as a infinite number. So think of it like a dial, a speedometer dial. So if this is my speedometer and I can track from 1 to 30, 60, 90, and then 120, and then let's say 150. But if let's say I am running a car, I can still track the speed, right? This or this. But if I'm tracking this same dial for a shuttle or a like aircraft, the speed will be above like let's say 900. So we will always see the upper limit. It will not show the max 900. It will not try to uh, like break this thing and show me 900. It's just going to show me the upper limit always, and it's saying, it will say that this is you have hit the max limit, so something like that. So the same thing is happening when we are calling this inf. So it's not a exact value, or it's not like the integer which try to consume the memory, but it is just a placeholder that tells Python that there is a very large value with a very large number, and you have to consider this number greater than any other number that is there. And so this is how it tries to tell. It does not point to the exact number. So if you add infinity to infinity, it will again tell you infinity. It won't give a certain number for that. So, and same applies to our uh, negative infinity as well. Now, if we try to compare infinity with some value, of course, infinity is going to be greater. So that's why it will return true. If we add some number to infinity, it is going to be infinity. Something that will merge in infinity will become infinity only. And if we subtract infinity to infinity, this is going to give me a null number, because we don't know this number, we don't know this number, then how we can subtract it, right? So that is why you can see these things are coming here. Now, if we want to check it for a nan, so again here it is like this way to represent nan, and we can check also whether this nan truly works or not. Nan is something like when we don't pass any value, right? If my sensor is not providing any value for let's say 1 hour, then there will be nan value, and we have to fill that value. And we often observe this case in the data science or machine learning problems to when we have challenging data and we have a lot of missing data, we use this method to identify the nan and fill those nans. So this is where like here I am using maths function of is nan to check whether it is true or not, whether it is actual nan or not. So let's try to run it and see. So initially, not a number is equal to not a number. So nan, basically nan equal to nan. So that is false. We can't compare two nans. Again, this is also a placeholder, not a value. And second, we are checking if nan is truly nan according to maths library. So this is saying, yeah, this is a nan. Now, there are two ways in which we can get nan again. This is one way like we defined nan. But if we calculate, so one is we already see, we subtract to infinity, we got nan. Second is if we divide to infinity also, we are going to get nan. Now, one more thing, let's try to see if we change the case, let's say if it works or not. It's a still working. So it's again insensitive to case. So yeah, this is all I wanted to cover around float. Now coming to complex, there is one more thing I wanted to cover. So in the complex numbers, you can see I have not compared it in my last videos, but in this advanced level, I am trying to compare two complex number as well. So for example, if I write this 2 plus 3j and 2 plus 3j, so is it going to be true? Most likely, yes. But what about this? If I use 3 in real axis and here 3 in the imaginary axis, and vice versa for this 2 also, like 2 is there for 2 is coefficient for imaginary axis and 2 is the number here. So is it also going to be same? Let's try to run it and see. You can say this is false while this is true. So it's not same. So why so? It's because it is trying to compare the values on the axis wise. So on imaginary and on this real axis, both should match. So that's why this 2 equal to and 3 equal to 3. That's why it's true and this is false. Now this is like just a comparison that whether they are same or not. This thing we have done, but can we do this greater than or lesser than comparison here? So that is not possible in this spatially complex number. So if I try to run this one, you can see Z1 and Z2. These are the two complex number. If I try to run this, it is going to fail. Again, why it's failing? Because there is no common ground on which we can compare this number. So if I just want to compare these two numbers, 1 and 2, we can easily say that 2 is greater than 1. And similarly, if I want to compare this 3 and 5, not j, then I can say 5 is greater than 3. But if I want to compare this versus this, what is happening is like we are not getting a perfect rule through which we can compare. Again, to explain that, first we need to understand like if we can compare this real number with this imaginary number, right? So let's say this j is nothing but let's say that j is greater than 0. Just a hypothesis. Now if we multiply this with j on both sides, so j into 0, this will become j a square greater than 0, which will be minus 1 greater than 0, because j is nothing but under root minus 1. So this is a wrong thing, right? This is not possible. Generally, 0 is greater than minus 1. This is reverse, so it's not possible. So this we can't make. Okay, let's try to assume the opposite. Let's say that j is less than 0. Now let's multiply both with minus j and see what is happening. So minus j square is less than uh, 0, let's say. Now this will become minus into minus 1 less than 0, which is 1 less than 0. Is it true? It is also false. 1 is always greater than 0. So both of these are not making a valid sense. So it is really difficult to define a common rule set which can be applied across this both real and imaginary number on which ground we can compare the value, and that's why we can't compare it basically, and that's why it is giving this error. Now let's try to see, like, it's not end of the world. We can still compare the value, but we have to compare it independently. Like we can compare the real values and the imaginary values separately. Now here is one case we are trying to compare the absolute values of these two. Now in this, if you check, the values are 2 here and 1 here. Then the absolute value, let's try to again print here z1 and z2. Print z1 comma z2. So this is my two numbers, and let's try to calculate the absolute value of this and see what is coming. So the absolute value of this is uh, 3.6, and absolute value of Z2 is 5 point something. So what is this? This is nothing, but you can think of it as a distance from 0 kind of thing. And that's where we can say that which one is higher or which one is lower. So we have seen it both, right? If not, let's try to print both and check. So you can see Z1 absolute value is lower than Z2. Here we are trying to compare the opposite. So let's see what we get. We are getting a false, which is correct. Makes sense here. I think this should be false. Now there is another way as well. So we have seen this real and image, through which we can extract the real values and the imaginary value of the complex number. So we can compare this way as well and try to see like what's the value we are getting. So what is happening here is, first it is checking if a real value of 1 is greater than 2 or not. So real value of 1 is 2, which is greater than 2. So that's why it is going in this loop. Then it is comparing the imaginary value of 1. So imaginary of value of 1 is lower. So this is it's going to return me false. Let's try to, okay, sorry. So here it's saying equal to, not greater than. So of course they are not equal, so it will go in this, and then when it will compare the real value, then real value is for sure like greater, and that's why it's giving you true. So this kind of logic can be built around complex number. Now I think uh, again, like if someone or if you are interested to learn more, there is like Python documentation as well. You can go in this website. I will try to load this notebook on my GitHub, and here you can see all the details related to my numeric data types. You can see here, and a lot of things you can find, the different functions, the different operations, and how the storage is there. So all the details you can find it here. You can try to go deep into this. You can also see the binary conversion, the bit count. So in very detail, you can see the other syntax also to define the integer that we have seen above. Like, so all those things, and due to lack of time, so I have just covered the important things that can be important or relevant and can be asked in interview as well. So yeah, this is all I wanted to cover in my today's session, and I know it's a little long, but let's try to wrap it up. And yeah, we'll see what we are going to learn in our next video, the another data type of Python. So with that, thank you everyone, and yeah, like, subscribe and share.